All right, I hope my screen is visible and I am audible. Somebody please confirm. Yes, thanks. All right, so this is where I ended yesterday's class. Um, we derived expression for acceleration of a fluid particle, that is at x at time t in Eulerian description. And this is what we got, uh, partial with time and then v dot del. Both operators should act on velocity vector, and the sum total of these two operations are going to give me the acceleration for that fluid particle. And again, reminding you that is not the same as just partial with time, right? That is just one contributor. So let's compare based on whatever we have learned about Lagrangian and Eulerian. Let's compare what seem to be advantage and what seems to be the advantage and what seems to be a disadvantage for these two methods or these two approaches. Okay, so Lagrangian, I'll just denote it with L. I've not written it every time. Eulerian E. So L is more intuitive because it chooses identified particles as independent variables. So that is more in line with whatever you have done so far in school or in recently in APL 100. Okay, so that seems like the obvious way you would also try to approach uh, fluid mechanics. So it's in line with what you have been trained, uh, the kind of training you have received so far in dealing with multi-member systems. Also, expression of rate of change following a fluid particle is simpler in L compared to E. So this also seems to be an advantage of L compared to E. Uh, Recall, if you have to find rate of change of anything, temperature, pressure, anything following a fluid particle, uh, which was at y at t equals 0, then it is just partial with time. Whereas if you want to find rate of change of any quantity following a fluid particle, and in this case you will have to you will be talking about the fluid particle which is at x at time z at time t. uh, that rate of change, if you want to find the expression, is longer. Not only it has time derivative, it has also advection operator, right? So Eulerian seems to be more complicated even for point number 2 that I have put on this slide. So based on that, it looks like we should use Lagrangian and it should be more popular, but it is not the truth. Eulerian is more popular. And the reason why Eulerian is more popular, because despite these two advantages that I mentioned, uh, once you try to have expression for net force acting particle, okay, net force will come because of two agencies. One will be a pressure force and the other will be viscous force. And we will see this in more detail in the coming weeks. But for the time being, we talk at this level that a fluid particle will be experiencing some pressure force and some viscous force because of the neighboring particles, right? And it turns out that in Lagrangian approach, trying to get that force is very cumbersome, is very complicated. Okay, so acceleration is fine, but getting the right hand side of Newton's second law in Eulerian is very difficult. And it turns out it is simpler in Eulerian, more difficult in Lagrangian and simpler in Eulerian. And that is why Eulerian is more popular. Okay, so let me elaborate a little bit about what I'm saying, why force is complicated. And I have put my best effort trying to put my ideas in words. I hope you get you understand what I mean to convey. So let's focus our attention on a specific chosen fluid particle, say S. Okay, this is where S is. And suppose we want to find the net pressure force on this particle S along E1. Okay, for illustration, let's just focus on E1 direction. What is the net pressure force acting on S along E1? Now, that we expect to be proportional. This is proportional sign. We expect that to be proportional to pressure that is associated with the fluid particle that is located to the left of S, right? That will try to push S towards right, minus the pressure associated with the fluid particle that is located to the right of S, which is here. That will try to push it towards left. Okay, so the difference between two pressure, we expect the net pressure force to be dependent on that, right? So if I try to cast this in terms of dependent and independent variables, this is the information we need to get force acting on S. What is this? We need pressure value at RSO. So RSO is the position vector of the fluid particle for which I'm trying to find force. I'm trying to write a governing equation. So RSO minus dE1 comma T. So this whole thing is nothing but pressure that is existing on this left green fluid particle, right? I'm assuming the two particles are separated by distance T. So I need PRSO minus dE1 at time T, and then I need PRSO plus dE1 at time T, which will be the pressure force associated with the right particle. Now you have to give it some thought, and I hope this sentence will appeal to you, that this information is readily available in Eulerian description, which has location as independent variable. So you can choose any location and Eulerian description will give you the answer of various dependent variables immediately. In this case, that dependent variable is pressure. So you query what is the pressure at RSO plus dE1. That is, Eulerian will give you a ready answer. Similarly for the right hand side. Okay, so it is easy to get the neighborhood information, neighborhood information of fluid particles in Eulerian, because you are not making first which particle, you are just saying whoever is at in the neighborhood, give me the value, and Eulerian is well suited to answer that question. Now think about Lagrangian. On the other hand, in Lagrangian description, we cannot access P at green location readily. Why? This is so because in Lagrangian description, you cannot access P directly by knowing the location. Here, by using the information, so what you will have to do in Lagrangian description, you know that you want pressure at RSO plus dE1, which is the right green particle. You will have to go and first seek solution of this equation, what I have written here. What is this equation? This equation is x plus, which is the current position vector of a fluid particle which was at y, but you want that fluid particle which has its current location at RSO plus dE1. So you know right hand side, you do not know y. Okay, and for that you will have to first, so you will use this equation to find y, and let me call that y that comes out as the solution of this equation as y star. So with this, so y star is the initial location of the particle at t equals 0, which is right now on the right hand side of my red fluid particle. So only when you have solved this equation and gotten y plus, then you can go and get this information P plus T comma y star to get pressure at RSO plus dE1, right? So this is a very roundabout method. You will have to kind of do data mining to get neighborhood information once you are putting your attention on a fluid particle. Okay. So because of this roundabout method of finding neighborhood information in Eulerian, finding pressure differences or anything which involves neighborhood information becomes difficult. And to find forces, you do need neighborhood information in fluid mechanics. The force that your fluid particle is experiencing, it depends on who is in the neighborhood. And that kind of puts Lagrangian on the back foot. It makes it more cumbersome, and Eulerian is a preferred choice. Okay, so we are saying in Eulerian, yes, expression of acceleration is complicated, but still we know it is still like an expression. You have to calculate more derivatives, but still you can get it. But the immense advantage that you have with forces, uh, because of that, we will choose Eulerian. Okay, so for the rest of the course, we will focus on Eulerian only now onwards. And we are doing it because it is indeed more popular. Most of the times we use that. I'm saying most of the times because there are some applications, advanced applications in fluid mechanics, where Lagrangian is also used. So it's not that we forget Lagrangian forever. There are some specific applications which are definitely outside the scope of this course. So we will not worry about it. But the whole idea of presenting this material was, in my mind, was to make you aware that there are two types of descriptions, and one is more popular than the other. I have given you some qualitative reason, and keep in mind that some applications still find Lagrangian useful. Okay. So now we are committing completely to Eulerian for this course. And just to remind you, independent variables will be xt, and dependent will be velocity, pressure, temperature, and rho, which make this set makes 6 scalar fields, right? 3 velocity components and 3, you can call them thermodynamic variables. All right. Okay. So now let's move on. I just want to mention it here that in some parts of my lecture, you will see that inadvertently, I don't mean to do this, but sometimes I write uh, R. I mean, there are three ways I end up writing R, this, and this. But please do not get confused. They all mean the same thing. I should be more careful to be consistent, but even if you do see different things, don't get confused. Similarly, it happens with me that I end up sometimes writing X as this, and sometimes as this. They mean the same thing. In fact, today's lecture, I have several such kind of packets of information or comments or definitions uh, that I will be sharing, and it is one of them. When a dependent variable is written as a function of space, uh, it is called a field. Okay, so sometimes I will say Eulerian velocity field at time t. So this is what it means. Field means I'm talking about a dependent variable which is continuous function of space x. I can also talk. I might have already used this phrase actually, Lagrangian velocity field. So that would mean v plus t comma y. So this is also space, even though it is not the instantaneous location, it is reference location, I mean position vectors at t0. Nevertheless, it is still a field because there is a dependence on space. So this is what is meant by field if this word comes out of my mouth at any time during the course. Now, if I have, if I have committed myself to using Eulerian description for a given flow field, say flow past an aircraft or flow past a building, I have committed myself for Eulerian description. It is actually possible to have to describe the motion using different reference frames, right? And you are very well aware of this last course mechanics. We often had multiple reference frames at our disposal, and sometimes we will measure velocity with respect to one frame, and then later we will go and try to find velocity of the same object, same body, same particle with respect to another frame, right? Same thing can happen here also. And I have an example here, a simple example. Suppose there is a flow field, which is white space on the slide, and the same fluid motion, the same fluid, or to even be, let's be even more specific, let there be a fluid particle L, and that is in motion, and that motion can be simultaneously be perceived by two observers, frame G and frame S, right? And the person who is sitting on frame G, he will measure the position vector from an origin which is fixed to its frame G, that fixed point is O here. And for the other observer, he would like to measure the position vector of the same fluid particle measured from a point O prime, which is a point fixed in his frame, right? So they will observe velocities of they will record velocity of particle L, but in general we know that in general these two velocities will be different. That's what I'm writing here, and here I'm putting this bar G and bar S to distinguish the importance of, or distinguish the fact that the velocities are being measured from two different frames. Again, I'm following the convention that is there in Dumir. Right. So the way I have shown the diagram, pay attention and understand this, that V at x comma t with respect to G and V at x prime comma t with respect to S both represent velocity of the same particle, because that's the way I have chosen. Okay, so the same velocity, the same particle is being observed, but its velocities with respect to two frames are different, right? And they are different, and how they are different, can we relate the two quantities? Indeed, we can relate the two quantities, and that relationship is exactly in accordance with the velocity transfer relationship that you must have derived and used multiple times in APL 100. So this is how the two velocities are related. So this is velocity of the particle L with respect to frame G, and here is the velocity of same particle observed with respect to S, right? And how are they related? They are related first. The first term here is velocity of O prime as observed from G. Okay, this O prime is fixed to S. So that velocity comes here, and then there is a cross product sitting here, and the first factor of the cross product is omega Sg. What is omega Sg? Is the angular velocity of frame S relative to G, and crossed with, so this is cross product, don't confuse it with X, cross product. The second vector in the cross product is X prime, which is basically R L O prime. Okay. So people who remember velocity transfer relationship, I hope they are agreeing with me. If you are still puzzled, then go back to your notes of APL 100 and see, it should be consistent with that. All right. So this kind of velocity transfer is important in fluid mechanics also, because here also we would like to change frames sometimes. So suppose an aircraft is flying, and so suppose an aircraft is flying, and I call aircraft as frame S, and G is let it be the ground. So what the pilot sees, so there is a fluid particle in front of the aircraft, then Vx comma Ts will be what the pilot sees sitting inside the aircraft, and sometimes we want to know that quantity, and on the other hand, sometimes we would like to know what is the velocity seen by somebody sitting on the ground. Okay, so this kind of situation can happen even in fluid mechanics, so it's good to be aware of this. However, from now onwards, the default reference frame will be ground. So unless I give you unless we have this peculiar situation of having multiple bodies, unless we have, the default will be just single frame. And even if I don't keep mentioning it every time, the default reference frame of observation will be ground. And further, I will also assume the ground frame to be inertial reference frame for the obvious reason, you would expect that at some point in time, I'm going to apply F equals ma on fluid particles. So for that, my reference frame has to be inertial. Okay, so if I'm not specifying, take that as default. Ground frame, inertial frame as the frame of reference. And also see, I will not keep writing this bar G every time, because this expression, you will see the PDs themselves are like very algebraically complicated. So we won't have enough space to put G. So G, even if this bar G is not there, as I said, it is implied, it is there. So Vxt is with respect to ground. Okay. All right. So now we will talk about, we will get to the next topic, which is fluid kinematics. And as you know, kinematics is description of displacement, velocity, acceleration, trajectory without any reference to forces. For maybe next three, four lectures, we will not make any reference to forces. We will just learn more about kinematics, how velocity and what is the significance of velocity or velocity gradient, such quantities in context of fluid mechanics. And that's why I'm segregating these 3-4 lectures under this heading, fluid kinematics. And also it follows the sequence of general mechanics. First you deal with kinematics, then you will bring in forces, and full dynamics you will have later on in the course. Okay. So under this heading, it is also pertinent to talk about what is called the graphical representation of a flow field. There are 3 different kind of curves which we generate, again based completely on kinematics, velocity, to visualize the flow field, right? To visualize the flow field, to give visual cues to the reader, what kind of flow field he's looking at. And my feeling is you might have come across this word in your school courses also. First is streamline. A streamline is a 3-dimensional curve. In general, it is a 3-dimensional curve. Some cases it is just a planar curve. In general, it is a curve in 3D space. So by 3D curve, I mean a curve in 3D space. Okay. In a flow field, so it is a curve is a 3D curve in general in a flow field at a given instant. So streamlines are drawn for a given instant. You take a snapshot of the flow field, take a camera shot of the flow field, and you can draw streamlines for that instant based on the information of the velocity field at that instant. Field at a given instant such that, what is the how streamline curves are defined? Such that the tangent vector at every point on the curve represents the direction of the velocity of the fluid particles that is currently present at that point. Okay, small arrowheads are placed on streamlines to convey the direction of velocity vectors. Sometimes streamlines are colored to show the magnitude of velocity as well. I will show it on the next slide, but for the time being, let's try to grasp this definition with the help of this example. So I have got this picture from internet, a simple flow field. So you have a wall which is like a sinusoidal going up and down hill kind of wall, and there is a flow field. There is air flowing above it. Okay, so if I don't show you any lines, it will be blank space, and I will say that there is fluid there, but you will not get any further qualitative idea. On the other hand, if I put these lines, which are individually called streamlines, so first velocity at this instant are oriented, right? Because I will go to this curve, say I go to this curve, rather this curve, you draw a tangent. You draw a tangent at that location, and that gives me the direction of the velocity of that fluid particle, which is right now occupying the point where you have drawn the tangent, right? So a simple graph like this, or a simple visualization technique like this, gives us a lot of information. Suddenly you start getting a feel of what the velocity vectors are at various locations, right? So this is an example of a streamline pattern at a given time instant, as I said. Another figure where I'm showing that sometimes people use streamlines to convey more information than just the direction. So direction, the information about direction is ingrained in the definition of a streamline. So like here, but people kind of make it more informative if they have access to such software or colored monitor or color printer. You can actually color the streamlines showing the magnitude of velocity. See here, there's a legend here. Blue color is it starts from 0 and red is the maximum is 1.1 and colors in between. So you can get a more quantitative picture of the velocity vector itself, the direction you had from streamlines, and now you are also getting magnitude information. Okay, so these are colored streamlines. Here there is an object and there is a flow coming, uniform flow, and it changes its direction. So I hope it starts, you'll agree with me that it starts making, giving you a feel of the flow field, even though the fluid particles most of the times are invisible themselves. Air is invisible and water is invisible, but plotting it like that helps. Okay. Now, some important aspects about streamline. A streamline is not defined at a location where velocity vector is 0, right? And this is because in the definition, it is ingrained that the streamline has to convey the direction of the velocity vector locally, right, of the local fluid particle. But when the velocity vector itself is 0, it has no defined direction. And that's why a streamline is not defined at those locations where you have velocity 0. The other important point is no two streamlines can ever intersect. If you see a flow field in which two streamlines are intersecting, then something is wrong, some data is wrong. Why? Because if you allow them to intersect, then at that point, whatever fluid particle is right now living or residing, uh, that will have it will have two directions of velocity. One tangent to first streamline, the other tangent to second streamline, which is physically impossible. So if you see a situation like this, be sure something has gone wrong. All right, streamlines can never intersect. Then we define, again, all these are for visualization of flow field or visualization of kinematics of fluid motion. So first is streamline. Sometimes we use what is called a stream surface. And a stream surface is a surface, not an, is a surface comprising of closely spaced streamlines. Okay. So if you put streamlines very close to each other, then you start getting a surface. It's just for enhanced visualization of the flow field. So that surface which will be made with these streamlines, closely spaced streamlines, will be stream surface. Okay. If we have a closed stream surface, it's called a stream tube, for example, like this. Okay, so again, these do not exist, of course, in reality. There is no tube. In flow, there are only particles moving, but for flow visualization, these aids are used. Okay, and since a stream surface, or for that matter, stream tube, which is a closed stream surface, they are actually made up of streamlines, closely spaced streamlines, and thus there cannot be any penetration through a stream surface. Penetration means fluid cannot pass through a stream surface. Right? I hope you agree with me. Why is that so? Because stream surfaces are made up of streamlines, and streamlines by definition are along the tangent of along the local velocity vector. Right? Streamlines have tangents along the velocity vectors. So it means that there cannot be any component of velocity of a fluid particle perpendicular to the tangent, to the streamline, and thus it is safe to say that no flow can pass through a stream surface, and in this case stream tube. So if you have a stream tube like this, you can actually kind of isolate this much flow from the other flow. By isolate, I mean that there cannot be any mass exchange between what is going through this imaginary stream tube and what is happening outside. Okay, and sometimes we use that idea for the simplification of equations. Uh, yeah, so this could be applied in some ways. It's an interesting concept for the time being for you. It is an interesting concept to be aware of. All right. So this was about streamline. The other visualization method is flow visualization method is what is called path line of a fluid particle. Path line. What is a path line? Path line, and then you see path line is of a fluid particle. Okay, so path line is associated with the fluid particle. Streamline is not associated with any special fluid particle. Streamline belongs to the entire space in which the flow exists. Okay, the streamline will be drawn in space at a given instant. Nothing special about a particular fluid particle. It has information about many fluid particles. Whereas path line is defined for a fluid particle. And how is it defined? Path line of a fluid particle is the trajectory of an identified fluid particle. That's all. So it is again closer to what we know about mechanics of particles so far. You have a fluid particle and you just trace its path, the trajectory. You remember this uh, uh, path coordinate system you must have learned. There we talked about trajectory, right? And that is what is the path line. Path line is simply trajectory of a fluid particle. So I have shown an example here. So at t equals 0, uh, say this particle, you name it, we give it a name alpha, and then at later times you will just keep tracking its path. I mean, you will just keep drawing that curve on which alpha travels, and you can continue this forever. You will get a path line of infinite length, depending on how long you want to track it. And I put a solid cylinder to show that why this particle will kind of change its path to negotiate around uh, the cylindrical surface, solid surface. Okay. The third visualization curve is the streak line. And streak line is associated with a location, with a location, just one location. Streamline was associated with the entire domain. Path line was associated with a fluid particle. Streak line is associated with a specific location. And what is the importance of that location? Streak line is the instantaneous time t locus of all those fluid particles which crossed an identified location, say L, in the past. Okay, so streak line has information about a set of fluid particles, where they are, their current locations. A set of fluid particles, where they are, you asked where they are, and then you connect their current locations with a curve, that is a streak line. But what is special about that chosen set of fluid particles? They all have crossed in the past. They have, at some time instant in the past before t, they have crossed a given specific location, which is L. Okay, so streak line is characterized by a location, right? These are the definitions. Okay, so the cross product is with x prime x plus vxt. It seems Jitendra's answer, Amitesh seems to be fine. Shall I keep going on, Amitesh? Assuming you have gotten your answer. Okay. So as I said, today's lecture has quite a lot of definitions. So I will keep hopping from one topic, one definition to other. A steady flow field. Again, you come across this phrase very often in fluid mechanics, and I think we should have clarity what exactly it means. A steady flow field. So field, I have told you what the field is. What is a steady flow field? So this is the definition. So all these six scalar fields, right? If all these six scalar fields, what I am highlighting here, velocity, pressure, density, and temperature, do not change with time. And when I said do not change with time, I'm talking about partial derivative. Okay. Over a time interval, say T1, T2. So suppose there is from 5 seconds to 10 seconds, you know that at no place in your flow field, or rather I should say at every point in the flow field, all these derivatives are zero. Okay, if from 5 seconds to 10 seconds, I'm confident that all these partial derivatives are zero, okay, then you can say that this flow field is steady from 5 seconds to 10 seconds. Okay, but all of them, these should be zero and at all locations. That's what I have written here. For all t element of x1, x2 and at all x. Okay. So it's quite a demanding, quite a demanding definition. And if any of these are not true, any variable has a partial derivative not equal to zero at even at one location and even at one time instant, then we should conclude that during T1 and T2, the flow field is unsteady. All right, one thing I need to highlight, see, when I say flow field, I actually include all these 6 scalar fields. Okay. If I say velocity field, then I will only mean 3 scalar fields, 3 components of velocity field. So I'm talking about a steady flow field. It means that all these 6 time derivatives, partial time derivatives should be followed for the flow field to be called steady over that interval T1 and T2. All right. Okay. Yeah, I'm including this slide in the notes here. I have written given you references which you may want to read pertaining to various topics that we have covered so far, right? So we covered tensors, and I would suggest that again for tensors, if whatever I have taught you, it is clear, you are able to handle the assignment 5 questions, then I would say for tensors, you don't bother about going to other books because uh, tensors notations, underbar, double bar, all they are very different in different books, and I think you will unnecessarily get confused uh, uh, further. So if you are clear, then don't go to any books. My notes are enough. If still you have a problem, then I suggest that you go to this book, Turbulent Flows. And I forgot to actually include the name of this book in the list of references in my course document. So, but I am putting it here. So it's a book by author S.B. Pope, Turbulent Flows. And there again, you go to Appendix A. That book has a lot more advanced topics, but you have to go to Appendix A to get information about tensors. If my notes are not clear, you may want to read, and that will hopefully clarify your doubts. Continuum versus molecular fluid mechanics and its application by Gupta and Gupta, Chapter 1. That's where you will find relevant material. Okay. Lagrangian versus Eulerian, again, you can go to S.B. Pope, Chapter 2, this book. Steady, unsteady velocity field and graphical descriptions, what I have mentioned so far in this today's lecture. GG means Gupta and Gupta. And the other topics that are coming in today's lecture, coming up in today's lecture or on Tuesday, fluid element change in size, again GG chapter 6, or FW is Frank White. The name of the full title of this book is there in the course document, so you can go to chapter 1 of FW, Frank White, or GG chapter 6. Okay. So this is what I was trying to distinguish in the previous slide, that when I say a steady flow field, then time derivative of all 6 scalar fields should be zero at all locations and all instants during that time. But sometimes we just say steady velocity field. Okay, and at that time, if I say steady velocity field, then my concern is only related to this partial derivative, which I'm showing here. The partial derivative of the velocity vector at all locations should be zero during that time interval. So this big what is this symbol, tau or gamma, I don't remember, but whatever this symbol is, that means the time period over which you are concerned, about which you are concerned, if the flow is steady or not. So earlier I was saying T1 minus T2, that is the same as this. I will correct this before uploading the lecture today. Now see, the interesting thing here is that whether the velocity field is steady or not, it actually depends on reference frame in context. And this may be a little surprising or a little less intuitive for some of you. So if you have two reference frames and there are two observers and they are looking at the same velocity field, okay, uh, it may happen that for one observer the velocity field is steady and for the other it may be unsteady. So whether when you talk about steady velocity field, keep in mind, be very clear with respect to which reference frame. And I have put a simple example here. You see, let's assume there is a boat moving very slowly in a pond, very slowly. I mean, there is a reason why I am putting it very slowly. And at some point after a month, I will come back and tell you what is the significance of slowly. For the time being, just take it as the way I'm telling you. And I still think that it will make some sense to you uh, when I ask you to visualize the flow field. So a boat is moving slowly in a pond which was otherwise stagnant. All right. So there is a stagnant. Uh, so for, if there is a boat here, it's moving. There is ground. On ground there is a person observing. So since I'm saying it's a pond, and it means that if the boat is removed, there is no motion, there is no flow, there is stagnant water. So all the disturbance that water body will experience, it's entirely due to boat. Okay, that's what I mean, which was otherwise stagnant. Now if you are observing the velocity field that is existing in the pond, now that the fact that boat is moving, uh, you will see an unsteady flow field. So this derivative at a generic point somewhere near the boat, say here where I have put this arrow, you will expect that to change. This velocity field will change, right? If the boat is far away from where your x is, you won't expect any disturbance. The velocity will be zero. But as the boat keeps coming nearer and nearer to this arrowhead of x, you will expect stronger, some velocity being generated in the pond, right? And that's why I'm saying that this observer will see a unsteady velocity field. All right. But now let's change the observer, or you being the observer, now go and sit on the boat. Okay. Now you will see what you will be interested in what independent and dependent variables. You will be interested in v with respect to b now, and your independent variables will be time, of course, and x prime. Okay. Uh, for this observer, this will be 0. V itself will be non-zero. Okay, but at a fixed location from where he is, that velocity will not change. So this is a case in which the flow field is, the flow domain is the same, but different observers, the velocity fields that they see, one is steady and one is unsteady. And again, here I'm not giving you any proof, anything. I do not have equations to give you the proof. I'm just appealing to your imagination and visualization. I mean, imagine yourself sitting in a boat moving in a pond. Uh, put your x prime at a fixed location. Why would you expect? So the fluid particle that is there at this instant, occupying the location x prime, you would expect it to have some velocity. And then at a later instant, 1 second later, your boat has moved forward, but you have kept x prime as the same. So there is a new fluid particle there occupying the arrowhead of x prime. But what is the reason why the velocity of that fluid particle be different from what you observed 1 second ago? It will not be. So that's why you will conclude that what you see is velocity field that you see is indeed steady. So keep this in mind. This is a very simple example, but for more complicated cases, having this clarity helps. So it will help us not to make mistakes later on. Okay, here what you see here, I'm not, it is there in the notes, obviously, I'm going to upload. I basically what the conclusion I'm making here, maybe I should put on the top. If the velocity field is steady, of course, with respect to some observer, in a steady flow field, path line of every particle, okay, path line of a particle and a streak line and streamlines, they coincide. Okay, in a steady velocity field, path line, streak line, and streamlines coincide. I'm making a statement here, and in the past I have tried to explain this in class, but despite me making attempts and using a lot of words, students I'm not able to convey clearly. So this time I am just leaving it on you, on your imagination. You convince yourself, think about it. That will be a good also exercise. I mean, you can think of this as a thought experiment. But I do want you to come in to be exposed to this statement. I will write that statement here at the top, that in a steady flow field with a steady velocity field, these curves all coincide. Okay. Next definition, three-dimensional velocity field. You will come across this reading fluid mechanics text. They call it three-dimensional velocity field, or they will call it two-dimensional velocity field. What does that mean? Three-dimensional velocity field means Vxt actually has dependence on all x1, x2, and x3. Whereas a 2D velocity field will depend on only two spatial coordinates. Okay. A velocity field which depends only on x1, x2, in x3 direction, it doesn't change, right? That is called a two-dimensional velocity field. It has dependence only on x1, x2, or it can have dependence on x1, x3, or x3, x1, but only two spatial coordinates change the velocity field. That's a 2D velocity field. And similarly, a 1D velocity field is one in which the velocity field changes only with one spatial direction. Okay. We will see examples of this. In fact, I am preparing you for examples, to exposing you with these phrases, because I will be bringing up such cases very soon. So just for reference, let's keep this in our notes and in our minds. Velocity field can be three componential, two componential, or one componential. Another description of velocity field. What is meant by two componential? Two componential will mean something what I have shown here, where I am moving my cursor. So velocity field has no E3 component. It has only one and two components. And those one and two components can depend on all spatial derivatives and time. We are not putting any condition on that. But the fact is that it has only the coefficient of E3 is 0. Such a velocity field I will call two componential. Or it has no even component. It has E2 and E3. Same thing, two componential. Or a velocity field can be one componential, in which only even component will be non-zero, or E2 or E3, only one of the three will be non-zero. And if none of these are there, then it will be in general three componential, right? In general. So I've talked about steady velocity field. I have talked about two-dimensional, one-dimensional velocity field, and I have talked about now componential, two componential and one componential velocity field. All right, fluid element. More definitions for streak line. Streak line, do we just join the... I'll come back to the question, Ankit. Let me cover one more slide, and then I will address your question. So another definition, we have a fluid element. Okay. So far I have talked about fluid particle. Now I'm talking about a new entity called fluid element. What is a fluid element? So far, we studied about a fluid particle, which is the smallest entity in continuum description. We considered it to be a point mass. While the concept of a fluid particle is useful in understanding the translational aspects of fluid motion, it is not adequate to examine other aspects like rotation, distortion, etc. Okay, thus we now introduce the idea of a fluid element, and I will use this acronym FE. Earlier it was FP, and now we have another quantity FE. A fluid element is a small piece of fluid comprising of numerous fluid particles. So it is a bunch of fluid particles that you are considering together, and this bunch is neighboring, adjacent to each other. So it's like you have now made in continuum description, particle was point mass, and now you are considering a small cube in continuum description. The size, and mind you, the size of a fluid element is small but finite, whereas fluid particle has no dimension. You may recall in continuum, in absolute sense it has, but that we have forgotten. In continuum, it has fluid particle has no dimension, but a fluid element has dimensions, even though small. This is what I have shown. And if you ask me how big in absolute scale, how big a fluid element would be, I will say that it will be, it will at least, it should at least have a dimension of 10 to minus 3 meter on either side. Okay. So what I'm saying that in absolute terms, effectively what I'm saying is that the dimension of a fluid element is at least 10 times the dimension of a fluid particle on absolute scale. You remember fluid particle, I was saying it has a dimension of 10 to minus 4, the size of a probe. So fluid element is 10 times of that. So you can well imagine that it has a lot of fluid particles inside it. Okay. And this is an example. And a fluid element, as part of its definition, has the same set of FPs at all times. So basically what a fluid element, as I said earlier, is a packet of identified fluid particles. So you have collected like 1,000 fluid particles you have identified, and you kind of put them in an imaginary wrapper, imaginary wrapper. It's like a chocolate wrapper. You have put them in 1,000 fluid particles in a wrapper, and you say that this is a fluid element now. Okay, that's the idea. That's actually that's the idea. And we want to do this because we want to have a body, because only when you have a body of finite dimension, even though small, you can talk about angular velocity, rotation, etc. Right? For particles, there is no idea of rotation. Particle has no orientation sense. It is dimensionless. So since we want to talk about rotation and deformation, etc., we are creating or defining this new entity, fluid element. All right, so I will get into more details about it in the next lecture on Tuesday, and let's go and try to address this question. For streak line, do we just join the current location of all those points which crossed a particular point to get streak line? Exactly, exactly. You join all the current location of all those points that in the past have crossed through that location which defines that streak line. Yes. May you explain both example again? Okay. See, what I'm saying here is in the first case, if you are the observer and you are sitting here and you are interested in mechanics of fluid, which is there in the pond, which is of course water, the fluid is water. What are you interested in? What velocity field you will be tracking? You will be tracking v x comma t, right? Where x is defined in this way. It is from an origin which is fixed to ground, and x is pointing to a particular location, and vxt will be the velocity of the fluid particle that is currently here with respect to g. I'm saying that that velocity will keep changing with time as the boat approaches this point. So you are keeping x as same, and you are observing, taking this data vxt at different times. So when the boat is far on the right, uh, you will see zero velocity, right? But as the boat keeps coming closer and closer, you would expect that the fluid particle will sense the motion of that boat. That's what happens, right? You go and you actually go in near a pond and see that if a boat is very far off, a kilometer off, and you keep your attention focused on a particle which is close to you, it will have zero velocity. But as the boat comes near to you, you will see that at that location you will start seeing ripples, right? So which means that in temporal history, velocity has been changing, and that's why I'm saying it is an unsteady flow field. I think this part is probably already clear to you, but I went over it. Now let's come to this case when you actually go and put yourself on the boat. So now really imagine, Jitendra, imagine that you are sitting on the boat, which is moving very slowly in a pond, and you focus your attention 2 meters in front of the nose of the boat. Okay, and at t equals 5 seconds, I tell you, please report the velocity of that particle, which is exactly 1 meter in front of you. What do you expect? You will report some velocity, right? Well, maybe it is 2 meters per second. It is 3 meters per second. Something you will report, right? At 5 seconds. Then after 5 seconds, I call you again on your cell phone and I say, tell me now what is the velocity of that fluid particle which is right now in front of you at the same distance which I asked earlier. That velocity, and I'm assuming the pond is very huge. I mean, you have not hit the boundary from going from 5 to 10 seconds. That is implicit assumption. So if the pond is very, very large, after 5 seconds, you would see the same velocity, what you reported earlier. There is no reason why it would be different. So if you would plot temporal history of velocity at a fixed location x prime at different time instants as seen by you sitting in the boat, that will remain constant. That will remain constant as long as the pond is very, very large and you don't need near the edge of or the boundary of the pond. So if you record like you make 5 such recordings and velocity is not changing, you can conclude that the flow field that you see is a steady flow field. All right, that's what the idea. I hope it makes sense. Did it help? Okay. After 5 seconds is the same fluid. No. Not at all, Satvik. After 5 seconds, the fluid particle has of course changed. There is a new fluid particle, but the moment, I'm assuming you are talking about the second situation in which the observer is on the boat. Am I right? Please confirm, then I will proceed. Otherwise, it will create more confusion. Yes. So in the second case, when you are sitting on the boat, at 5 seconds, I probed for a data and you told me over the phone that you measured velocity of particle alpha, which was 1 meter right ahead of you. After 5 seconds, I call you again, that is at 10 seconds, and I ask you, tell me the velocity of whatever fluid particle is there in front of you at the same distance as before. So at that instant, of course, alpha is gone. Alpha is gone in the wake. It is somewhere behind. It is beta. It's a new fluid particle. But that fluid particle, since it is lying at the same location and as seen by you, you will see the same velocity. That's what my claim is. Okay, and my claim here is just relying on, I mean, convincing you. Well, I'm convinced it will be the truth, but if you and I'm confident because I know the equations. I'm aware of the equations. I've seen solution also, but I know you have not seen the equation. You have not seen the solution. But I'm just appealing to your intuition right now. Nothing more than that. Satvik, does it make sense? Yeah, so again, if since I'm appealing to your intuition and your intuition is not convincing you, then I would say don't worry then. Don't worry because at best you can use your intuition right now. And if still not making sense, then wait for a few more weeks. I'll come back to this. I'll come back once we have the equations. I will then convince you with equations. All right. Okay. Yeah, I will be here for 5 more minutes. I've extended the class so that it doesn't end abruptly. Okay, Amitesh, are you there? Yesterday I was trying to respond to your query and it ended abruptly, but then I sent an email to you. Have you seen that? Okay, I hope that helped. Did that help? Maybe not. Yes, it did. Okay. Yeah, since you didn't reply back, I was not even sure I have sent it to the right Amitesh. I just remembered your first name. So good that you have received, and yeah, hope it helped in some way. No, that's okay. It's fine. All right, it seems there are no further questions, so I am ending this session and we will meet again on Tuesday.